Hi everyone. In this video we're going to consider gas transport through the systemic circulation and then the gas exchange at the peripheral tissues. So we remember that gas exchange occurs at the alveoli. Oxygen, which is in high pressure in the alveoli, diffuses into the capillaries, and CO2 from the capillaries diffuses into the alveoli. So in order to speak about the gas transport through the plasma, we need to talk about red blood cells a little bit. So red blood cells contain hemoglobin, and hemoglobin is abbreviated HB and HGB, different in different books, so I'm just going to write both of them, and for clarity I'll use HGB in this video, but they're largely interchangeable. So hemoglobin is a molecule that contains 4 protein subunits. And in normal adult hemoglobin, we have 2 alpha chains and 2 beta chains. And each chain has a heme group or a heme component, and heme contains iron, which basically is what binds the oxygen. Each heme is able to bind 1 oxygen molecule, and there are 4 hemes per hemoglobin molecule. So 1 hemoglobin molecule can bind 4 oxygen molecules. For each red blood cell, there are about 280 million molecules of hemoglobin. So the amount is astronomical in terms of when you consider how many millions of red blood cells there would be transporting the oxygen. And so the red blood cells, the capillaries are very, very small. And so one red blood cell, like the diameter of one red blood cell, fits about in the capillary. And oxygen is actually able to cross the alveolar capillary membrane and dissolve in the plasma and move into the hemoglobin in about 1/4 of a second. So the gas transfer is extremely fast. That's the amount of time, 1/4 of a second, for equilibrium to be reached in terms of oxygen diffusion across the membrane. And then those oxygen carrying red blood cells are swept away and the next ones arrive, and it continues. So the process is very, very fast. So most of the oxygen is transported in the blood bound to hemoglobin. About 98.5% of oxygen is bound to hemoglobin for transport, and then the remaining oxygen is transported dissolved in the plasma. So this is a good time for us to talk about SpO2. So SpO2 is pulse oximetry. It's a measure of how much hemoglobin, what percentage of hemoglobin is saturated with oxygen. And this is really, really important. It does not go the other way around. So what a lot of people will say is that it's how much oxygen, like what percentage of oxygen is bound to hemoglobin versus the percent that's not. 98.5% is how much is bound to hemoglobin, and then about 1.5% is not. But when we talk about the SpO2, we're talking about how many molecules of hemoglobin, what percentage of those molecules have something bound to it. So most of the time we're talking about oxygen, but a good comparison would be if we were to talk about carbon monoxide, CO. CO binds where oxygen binds, and it has an affinity that's about 200 to 300 times the affinity that oxygen has. So when we think of carbon monoxide being bound to hemoglobin, it's going to get us a falsely high reading of the SpO2 because the SpO2 is just measuring hemoglobin and hemoglobin with something attached. All right, so once the oxygen is bound to the hemoglobin, it's going to travel in circulation and it's going to arrive at peripheral tissues. So the one point I want to make about this is that arrival in the peripheral tissues means that when we actually have oxygen offloading or unloading from the hemoglobin, it's happening at the capillary level. So once again, in order for oxygen to diffuse, it has to be diffusing a very short distance. And so the short distance is one layer of cells that is the capillary wall, the endothelial cells, and then into the interstitial space, or maybe the tissues are directly bound and the oxygen will leave and enter into those peripheral tissues. And one thing that's really important about that we're going to expand on in a little while is that as the metabolic activity increases, in particular, we expect to have high metabolic activity in peripheral tissues, we actually get increased unloading of the oxygen. So it's a really important point, but we're going to expand on that in just a moment. where this leaves us is we want to talk about something called the oxyhemoglobin dissociation curve. Now, I don't know how you feel about graphs, but I particularly hate them because I think they're kind of hard to figure out. But this one is really, really important, so we're going to spend a little time looking at it. So we have a y-axis in the vertical direction and then an x-axis in the horizontal direction. And on this particular graph, in the horizontal direction, we have PO2, the partial pressure of oxygen in the blood. And then on the y-axis, we have SpO2, which is the percent of hemoglobin that's saturated with oxygen. And so I just want to make a quick point about X versus Y. The X-axis contains the independent variable, and the Y-axis contains the dependent variable. So that means that the SpO2 depends on the PO2. So as the PO2 changes, the SpO2 changes accordingly. So we'll just measure on the x-axis, we're going to measure the PO2 in millimeters of mercury, and then on the y-axis, we'll measure the SpO2 in percent saturation. So just as we mentioned, the hemoglobin saturation is dependent upon the PO2 in the blood. And so one thing that we really want to pay attention to here, and this is kind of, this is probably one of the most important points about the oxyhemoglobin dissociation curve, is that, and we drew some green lines at 60 for PO2, 90 for SpO2, and we show the intersection on this little curve. And so that's kind of our marker for good. Above is better. And so here's the statement, if PO2 is greater than 60, then the SpO2 will be greater than 90%. So oftentimes, if the PO2 is less than 60, we can consider that likely to have an association with tissue hypoxia, and if it's greater than 60, then probably not. So if the PO2 is at least 60 millimeters of mercury, then the SpO2 is at least 90%. However, if the PO2 drops below 60 millimeters of mercury, then the SpO2 drops rapidly as well. So let's try and illustrate this point. I like to think of this curve as a slide, and this person is sitting at the top of the slide, and you notice that it's almost kind of flat. There's a little bit of an incline, but it's almost kind of flat. So if we're sliding down that slide and kind of like before we get to the intersection of those green lines, it's possible that you could stand up and kind of walk back up towards the top. So it's kind of like if you're above 60 millimeters of mercury for PO2, then you're pretty safe. The SpO2 will remain high. But if we were to pass that threshold, and now we're kind of in this steeper portion of the curve, right? There's kind of like a point of no return there, where when you get kind of beyond that threshold, you really can't stand up and climb back up the slide. You are definitely committed to going down. So it's kind of like that with the PO2. If the PO2 drops below 60, then you're pretty much committed to dropping your oxygen saturation. That's pretty much going to happen. So here's the relevant example that I think is the easiest to sort of think about how this could actually occur, and then we're going to expand on some other concepts regarding this. Let's say that you're going to intubate somebody. So this person initially is receiving assisted ventilations or ventilations via bag valve mask, and the PO2 is being maintained because oxygen is being delivered via bag valve mask ventilation. But as soon as you remove that bag and you perform direct laryngoscopy, the PO2 is definitely dropping because no more oxygen is entering into those lungs at that point in time. There's a point of it being kind of stagnant. And so immediately you're going to start to drop your PO2, but maybe you started with a PO2 of 100 and you have a little room, right? So if your PO2 was 100 or your PO2 was, 95 or 90 or something like that, you have some room before you get to 60. So when we think about, taking no more than 30 seconds to perform direct laryngoscopy and pass a tube, we're saying that what we don't want is to cross that threshold where the PO2 is dropped below 60 and we don't have any backup because we're not actually ventilating the patient at all. And so once you get kind of below that, you'll watch those oxygen sats just completely plummet, and it'll be much more difficult to recover. So it's very important to sort of, to first of all, to provide adequate ventilation so that the SpO2 is above 90, but also to ensure that the break that you take to perform direct laryngoscopy is short enough that you are not dropping below that 60 threshold, so that your SpO2 is recoverable even if it drops to 90 during the intubation. All right, so now let's talk a little bit about something called cooperative binding. So cooperative binding, so we mentioned that we have 4 hemoglobin subunits, and so we can actually bind 4 oxygen molecules to the hemoglobin. So we see that we have little seats for each one of them, right? And so basically cooperative binding says that when we have one oxygen molecule that binds to one of those 4 subunits, we have a conformational change, a change in the shape of the molecule that actually increases the affinity of binding for an additional oxygen molecule. So when we have one oxygen molecule bind, we change the shape a little bit, the next one binds. We change the shape a little more, the next one binds. We change the shape a little more, the last one binds. So as we increase the amount of oxygens bound to a hemoglobin molecule, we increase the affinity for subsequent oxygens to bind, making it significantly easier. So if you were to just pop off one of those oxygens, you want to bind it again, pretty easy to get that oxygen back on. But when you really kind of empty out that hemoglobin molecule completely and you're down to just 1 or 0, it's a lot more difficult to attach those oxygens once again. So this mechanism is actually connected to the properties of the plasma. So for instance, pH is a really good example. So when you have a decrease in pH, you actually get a decrease in the binding affinity. And as a result, you'll have an increase in the unloading in the peripheral tissues. So this is, I want to kind of just mention that these things that we're discussing are not necessarily bad. When we talk about disease, they play a role, but in normal physiology, these things are also important to sort of maintain function. In the alveoli, we don't necessarily have metabolically active tissues. That's what we're going to say about the peripheral tissues. So in the alveoli, we're likely to have a higher pH, which means that we have easy loading of the oxygen, which is what we want. We want for the red blood cells that are passing through the pulmonary capillaries to have an easy time collecting that oxygen from the alveoli so that it can travel that oxygen anywhere in the blood where it needs to go. And then when we arrive at the peripheral tissues, we're actually going to experience a lower pH. So that lower pH is largely due to an increase in CO2. So the metabolic activity of the tissues is going to produce CO2 as a byproduct. And so we'll have a bunch of CO2, and we know based on the carbonic acid bicarbonate buffer system that increased CO2 means increased H+. So we have a lower pH, which means we have easy unloading of the oxygen, which is also what we want. When the oxygen arrives at the peripheral tissues, we want it to be easy for it to transfer to those tissues for use, because we know that the oxygen is needed to make ATP. The oxygen is needed for survival of those peripheral tissues. So if we don't have oxygen delivery, then we don't make ATP, and then we can't power our sodium-potassium pump, and then the cells are going to die. So everything kind of relies on the ability of the oxygen to not only easily load at the alveoli into the red blood cells of the pulmonary capillaries, but also to easily unload at the peripheral tissues so that the efficiency of tissue energy production can be maintained. So I just want to write the carbonic acid bicarbonate buffer system real quick. I know that we're going to do this a few times in this video, but just as a reminder so that we could see the association for why increased CO2 in the peripheral tissues leads to an increase in H+. And also, I just want us to keep in mind that when we have things like decreased CO2 exhalation, so if you're not breathing or you're not breathing well, you're going to build up your CO2 in the pulmonary capillaries in that area, and so we're going to have an increase in the hydrogen ion concentration there. And I just want to mention that to set us up for what we're going to talk about next, which is shifting of the oxyhemoglobin dissociation curve. So the first thing we'll consider is a right shift. So basically what we're saying is we're taking this line and we're literally moving it to the right just a little bit. And what that means is that we're going to line up with different numbers when we compare the PO2 and the SPO2. So with a right shift, let's talk about why we get it, first of all. So an increase in CO2, an increase in H+, or a decrease in pH, an increase in temperature, and lastly, an increase in 2,3-DPG, which is diphosphoglycerate, 2,3-diphosphoglycerate. Those things are things that will cause a right shift. Now, and I know that we haven't really ever talked about this before, but 2,3-diphosphoglycerate is something that is increased with increase in metabolic activity. So like, for example, red blood cells that don't have mitochondria but are performing anaerobic metabolism, so they're basically making a tiny bit of ATP without any oxygen. Those guys are actually going to produce 2,3-diphosphoglycerate. These things, all of these things, will lead to a decreased binding affinity of hemoglobin for oxygen. And what that means is we need a higher PO2 to maintain our SpO2. So let's take a look. So the first red line that I drew is, now we can see in the vertical direction, is lining up with the 80. So what we're basically saying is that with this right shift, and I'm not saying this number is exact because I think the shift can kind of be variable in terms of how much, but if you have a right shift, and let's just say, for example, that we're at 80 now, the PO2 has to be 80 in order to have an SpO2 of 90. And then if you drop below 80, that your SpO2 is going to plummet kind of fast. When we think about what's going on in the peripheral tissues, meaning we're increasing our CO2 concentration due to metabolic activity, we're sort of generating this right shift situation. We're making it possible for the hemoglobin to easily offload. But what we don't want is for oxygen loading at the alveoli to be difficult. So normal physiologic conditions, we expect that we're going to have decreased binding affinity in the peripheral tissues. What's bad is when we have poor binding affinity at the alveoli, because that means that we're not going to take the oxygen from the alveoli and bring it to where it needs to go. All right, so now let's talk about the opposite. Let's talk about a left shift. So now we can see the blue line is, now we're kind of moving the graph to the left a little bit, and it's going to be completely opposite. So a decrease in CO2, a decrease in H+, a decrease in temperature, and a decrease in 2,3-diphosphoglycerate, all those things opposite of right shift are going to cause a left shift. And what we get is an increased binding affinity for oxygen. And so what this means, let's think about this, is that when we arrive at the peripheral tissues, now if we take a look, we only have to have a PO2 of 40 to maintain our SpO2 of 90. It's going to be much more difficult for us to unload the oxygen where it belongs in the peripheral tissues. Now let's just talk for a moment about what happens with carbon dioxide transport. So carbon dioxide can be transported in the blood in 3 ways. 1, it can be dissolved. 2, it can be bound to hemoglobin. Or 3, it can be converted to bicarbonate ions. All right, so here is our red blood cell, our peripheral tissues, our CO2 that's being produced in the peripheral tissues, and then we'll talk about what happens. So option 1, we simply dissolve in the plasma. So CO2 just transfers into the blood and off it goes. It's just along for the ride. And remember that the solubility of CO2 is much higher in the plasma than oxygen, so it's a little bit easier for this to occur. So about 7% of the carbon dioxide is actually transported dissolved in the plasma. The next option is that the carbon dioxide is transported bound to hemoglobin. So hemoglobin actually binds carbon dioxide just the same as it binds oxygen, but they bind to totally different binding sites. So it's not the same thing as carbon monoxide binding to the same binding site where oxygen binds and then preventing oxygen from binding. This is not an interference. The binding occurs to totally different sites. And however, the more oxygen that's bound to hemoglobin, the lower the affinity the hemoglobin has for carbon dioxide. So this is great because when we are in the pulmonary capillaries near the alveoli, we're going to have really good oxygen loading, and carbon dioxide is not really going to interfere, and it won't necessarily bind. And then when we arrive in the peripheral tissues and we have oxygen unloading, now we can actually increase the affinity for CO2, and the CO2 binds easily. So about 23% of the carbon dioxide is transported bound to hemoglobin. And the last option is that we use the carbonic acid bicarbonate buffer system to convert the CO2 to bicarbonate ions. And this buffer system exists both in the plasma and in the red blood cells. So we can see that in the plasma, we have CO2 that's converted to bicarbonate ions, and the bicarbonate ions is basically transported in the plasma. And then if we look at the same equation in the red blood cell, the major difference in the red blood cell is that we have this enzyme that actually sort of works on the conversion of CO2 and water into carbonic acid. It's called carbonic anhydrase. So carbonic anhydrase is an enzyme that catalyzes the conversion of CO2 with water to carbonic acid. So it basically dramatically increases the rate of conversion. So the same thing happens in the plasma that happens in the red blood cell. It just happens faster in the red blood cell because we have this enzyme. And then again, we produce the bicarbonate ions, and of course we're producing H+. So a couple things have to happen here. One is we actually are going to take that H plus and bind it to hemoglobin. So we have to buffer the H plus. And since we're moving in the opposite direction here, we're not buffering the H plus by making CO2 because we have more CO2. So based on Le Chatelier's principle, the direction of movement in this equation is to the right, meaning to make more H plus. We're going to find another way to buffer that H plus, and that's binding it to hemoglobin. And then the bicarbonate ions actually move into the plasma, so out of the red blood cell. Now, of course, if we move a bicarbonate ion into the plasma, what that means is we're moving a negative charge, and so we use a little chloride shift. We move a chloride ion in, and we have a negative for a negative, and everybody's happy. So this is what happens in the periphery. We're going to travel the red blood cell and the blood with all the carbon dioxide in it. Oh, and by the way, 70% is transported as bicarbonate ions. So we're going to travel to the pulmonary capillaries, and at the pulmonary capillaries now we need to get rid of all our CO2, and since we said that 70% is actually transported as bicarb, now we have to convert it back. So now we're going to do the equation in the opposite direction, and we're actually going to make the CO2 from the bicarb, and then we're going to exhale that CO2, and the process begins again. We pick up the oxygen and we travel to the peripheral tissues. So that is gas transport in a nutshell. I hope you enjoyed it. Our next video is going to be about control of respiration. That's all for today. Thanks for watching.